All right. Since we have 2 minutes left, so maybe please allow me to deliver the beginning speech of this AT1 session of MG16 meeting. Well, I have to say, since as always as the previous MG meetings, this meeting is again organized in the summer, but this summer is a very very special. We are not doing the meeting face to face, which is a huge pity. And at the very beginning, I thought it would cool down our, our enthusiasm about this meeting. But eventually, it turned out that there are so many people doing the registration and wanted to deliver the talk. And at the end of the day, as the chairperson of the main part of this session, and my colleagues and I made a huge efforts by selecting the topics, which doesn't mean those talks which was not selected were not good. They are actually still as good as the selected ones. But yeah, it's totally due to the limit of the talk numbers. So okay, it is so welcome to see all of you guys. Maybe I can show up my face a little bit. Well, let me check if I dressed fair way. Okay, great. Right. Hi everyone. It is very nice to welcome you to join this AT1 session. It's the alternative theory and the quantum cosmology perspective. And our first speaker is Dr. Marek Liska. Can you please share your screen now?
Of course.
Yes, please.
I'm on it.
So today it will be Dr. Wentao Luo, Amara Elias, and I to co-host today's session. I hope you enjoy this session, the talks of this session, the same enthusiastic as the Europe Cup and the America Cup, I guess. All right, yeah, let's begin.
Okay, hello. Thank you very much for the opportunity to give this talk. It's based on a work I carried out together with my supervisor, Dr. Ana Alonso Serrano from the Max Planck Institute, and it's concerned with the relation of low energy quantum gravity dynamics and thermodynamics of space-time. It is well known that gravitational dynamics imply a series of laws for black hole mechanics that are analogous to the laws of thermodynamics. Now, in 1995, Jacobson showed that you can actually turn this reasoning around. That is, by assigning entropy and temperature to locally constructed causal horizons and studying their thermodynamics, you can derive gravitational equations of motion. I will review this result briefly at the beginning of my talk. Now, it is also well known that when you consider low energy quantum gravity corrections, the formula for horizon entropy is modified. And the main question I will try to answer today is whether and how precisely this in turn influences gravitational dynamics. Now, the main reason why to even try something like this, we believe, is that in pretty much all the main candidate theories of quantum gravity, there is the same form of modified entropy. Therefore, this allows us to obtain general low energy phenomenology of quantum gravity, whose physical implications, especially of course to cosmology and black holes, are model independent. I will discuss some of these implications at the end of the talk on a simple toy model. So first, I will briefly recap the derivation of equations of motion from thermodynamic in semi-classical setting. For this, one first needs some notion of local causal horizon that can be constructed in every space-time point. Originally, Rindler wedges were used by Jacobson, but in our case, geodesic local causal diamonds are actually more convenient. These are very simple objects. In any space-time point P, you choose an arbitrary time-like vector n, and in every direction orthogonal to n, you send out of P geodesics of parameter length L. These together form a geodesic ball, sigma 0, and the region causally determined by sigma 0 is our causal diamond. So it's completely determined by the choice of a time-like vector and the length scale. You can show that the null boundary of this causal diamond is in fact a conformal killing horizon corresponding to this conformal killing field. Therefore, one can assign Hawking temperature to it, and with a specific choice of normalization of this vector like this, you get this simple relation h bar over 2 pi for it. Furthermore, the entanglement entropy associated with this conformal killing horizon is just proportional to its area with undetermined proportionality constant. Now we have this basic geometric setup, and there are two main approaches to obtaining equations of motion from it. One of them is a physical process one, in which we study matter flux across the horizon and corresponding changes in its area. The other one, newer, is based on the entanglement equilibrium hypothesis. It starts with the equilibrium state of the ball sigma 0 and considers small simultaneous variation of geometry and fields. I will only further comment on this second approach. The first one in almost most important points is equivalent and leads to same conclusions. So the entanglement equilibrium derivation. The equilibrium state we start from will be simply a Minkowski spacetime. So in complete vacuum, no spacetime curvature. And we will allow variations of the metric, all the matter fields present, and also the cosmological constant. But all these variations will be carried out at fixed spatial volume of sigma 0. Now, assuming that this was initially equilibrium, for a small variation, we get that the sum of the change of entropy due to changes in geometry and due to changes in matter will be 0. For the changes of entanglement entropy due to geometry, we simply have that they are proportional to change of area, which can be easily expressed in terms of Einstein tensor and change in cosmological constant. For matter, we have a simple formula for the change of entanglement entropy in the case of conformal fields. Then it's just an integral of the quantum expectation value of energy momentum tensor divided by temperature. And after integration, it's this simple formula. For non-conformal fields, things are a little bit more complicated, but as long as the theory has an UV fixed point, it can be shown that the variation of matter entropy is almost the same as for conformal fields, but with additional contribution of a spacetime scalar delta x that in general can depend on the diamond size L. So we put together the variation of entropy due to geometry and due to matter, and the resulting equilibrium condition is this one. We can obtain precisely the same condition for any choice of a time-like vector n. That choice was completely arbitrary at the beginning. So we can just get rid of this contraction with a time-like vector and find tensorial equation that you can see already somewhat resembles Einstein equations, except there is this additional delta x terms coming from non-conformal quantum fields. To get rid of this, we can simply take trace of this equation and from this find an expression for the variation of cosmological constant. Furthermore, we will use this eta present in the definition of entanglement entropy to define the Newton gravitational constant, essentially by demanding consistency with Newtonian limit. And it reads G is 1 over 4 pi h bar eta. with this choice, it actually turns out that the entanglement entropy of diamond's horizon is precisely given by the Bekenstein formula. So it's area over 4 times Planck length square. And with these choices for variation of cosmological constant and for value of eta, we recover traceless equations of motion in this form that you can notice, first of all, are semi-classical because they contain expectation values of energy momentum tensor rather than its classical value. And secondly, they are more consistent with equations of motion of unimodal gravity than general relativity. In one of our papers, we actually argue that this is not something superficial and that indeed thermodynamics of spacetime generically leads to unimodal theories of gravity, but I have no time to go into details of this argument. Now, this is all done in one spacetime point, but invoking the equivalence principle, we get this form of the equations of motion valid in every spacetime point. This was all done with Bekenstein entropy, and we obtained standard unimodal gravity, but it can be done for many local diffeomorphism invariance theories of gravity, just switching the Bekenstein entropy with the appropriate Volt entropy. What we tried to do was going one step further and introducing leading order quantum gravity corrections to Bekenstein entropy. These are non-local, logarithmic in horizon area, and accompanied by some number C that is generally believed to be of the order of unity, but its precise value and even sign are model dependent. I should stress that this form of entropy is valid only in 4 spacetime dimensions, and it's actually non-trivial to try to do our reasoning in a different dimension. We haven't tried it yet, and it's certainly not just some simple generalization. Now, the important point, as I stressed in the beginning, is that this form of modified Bekenstein entropy is very general. It comes from loop quantum gravity, ADS-CFT correspondence, generalized uncertainty principle phenomenology, and calculations of entanglement entropy, even from non-local effective field theory. These all just differ in the precise value of C. And importantly, the modified entropy of this form only occurs for closed horizons. And that is the reason why we chose to work with causal diamonds rather than Rindler wedges, which are not closed. So we take the modified entropy, we plug it into thermodynamic derivation. It goes along the same lines as in semi-classical case, but of course it's much more involved. But in the end, we obtain modified equations of motion of this form. Here, S is just a shorthand for the traceless part of Ricci tensor. On the right-hand side, we have traceless part of the expectation value of energy momentum tensor. And on top of that, there are some correction terms quadratic in curvature tensors, multiplied by Planck length squared and some number d. This d can be directly obtained from the C present in modified entropy. It is of the same order of magnitude, and importantly, it has the same sign. Now, these equations you can check are traceless, which again reminds us of unimodal gravity. They are clearly nonlinear in second derivatives of the metric, but at the first glance, there are no higher derivative terms. Of course, that's a little misleading since these are implicitly present in the definition of this expectation value of energy momentum tensor. And importantly, this equation is not divergence-free. So in general, it will be incompatible with local energy conservation. Of course, in some highly symmetric cases, that won't be a problem, and we can have local energy conservation, just not in completely general situations. So these are the general equations we found, but to discuss their physical implications, we should go to something simpler. And for that, I chose a very simple toy model, homogeneous, isotropic, spatially flat cosmology with perfect fluid. So this is described by well-known Friedman limit Robertson-Walker metric. And as I noted the similarities of our theory with unimodular gravity, I choose it in its unimodular form. Plugging it into equations of motion, we find only one non-trivial condition, a modified Raychaudhuri equation that contains a correction terms that goes as time derivative of Hubble rate squared and multiplied by d Planck length squared, the same way as all the correction terms in the general equations. This is still fairly difficult to analyze. It's nonlinear in second time derivatives of the scale factor. So to simplify it, we rewrite the correction term using the standard Raychaudhuri equation. It's of course non-trivial that you can do this, but we are only interested in getting some glimpse of the dynamics. So we will just try it and see what happens. So we get this form of the modified Raychaudhuri equation where the correction term is stated in terms of matter variables. And to move further, we need to make some assumptions about our perfect fluid. I choose this very simple equation of state and further demand that energy is locally conserved. While, as I said, this is not possible in general for our equations, in this case, due to symmetry, it is not a problem. And we will find this condition on energy density just as we do in standard general relativity. Plugging this into modified Raychaudhuri equation, we can now integrate it and obtain modified Friedman equation. There appears an arbitrary integration constant, which we can identify with the cosmological term. This is a feature that really is very similar to unimodular gravity, where also you get cosmological constant only as an integration constant from the energy conservation. So this is our modified Friedman equation, and now a few words about what it implies. You can notice that as long as D is positive, this looks exactly like effective dynamics of loop quantum cosmology. Therefore, it implies that Big Bang singularity is replaced by a regular bounce, which corresponds to some critical density that for dust has this form, Planck density over 2 pi d, and since d is more or less order 1, this is definitely a Planck scale effect. Of course, all this only holds if d is positive. So if that means the correction term in Bekenstein entropy must be also positive. It must increase the entropy. Otherwise, we don't get singularity resolution. So to sum up, we have found general modified dynamics, assuming only that Bekenstein entropy contains a logarithmic term in horizon area. And we have seen that at least in a very, very simple setting, this modified dynamics is sufficient to resolve singularities. Now, let me say just a few words about what we are going to do and doing now. First of all, we need to perform a deeper analysis of our modified dynamics. Of course, especially in regards to energy conservation and related issues of diffeomorphism invariance and non-locality. It would be interesting to see whether these equations are stable with respect to perturbations and clarify the precise role of higher metric derivatives. Secondly, we would like to see whether the entropy corrections are indeed positive, as our theory demands to resolve singularities, and if so, for what approaches to quantum gravity that is the case. And lastly, we would like to deepen the connection between thermodynamics and unimodular, or more precisely, while transverse gravity, even in purely semi-classical setting. Okay, that is everything from me. Thank you very much for your attention, and I look forward to questions.
Yeah, thanks, Marat. I think we have time for 1 or 2 questions, please. raise your hand or just directly ask. So are there any questions? Okay, so if no question, Mark, could you please stop sharing and then let's
Yes.
move to our next speaker, which is who
Okay.
is Gilberto Silva, and his topic is going to be cosmic string-like objects in the hybrid metric Palatini gravity. Please
Hello,
take it away.
good morning.
Can you
Uh,
share your screen?
yes, I'll share my screen, see if everything goes right.
Oops, sorry, I cannot see your screen.
It takes 1 second.
Okay. Oh, great.
Can
Yeah.
you see it now? So I'm going to put it
Yes.
in full screen mode.
Yeah, great.
Okay.
Thanks.
Okay. So good morning to everyone. First, I'd like to thank the organizers of the meeting for the opportunity, and of course to the conveners of this session for the opportunity to present my work. So my name is Gilberto Silva. I'm a master student at Instituto de Astrofísica e Ciências do Espaço in Portugal, and this is part of my master's thesis that I'm conducting with Francisco Lobo and Pedro Avelino. And this work was also done with the help of Tiberio Arco, invaluable help in finding the some of the solutions. So I'm going to talk about cosmic strings in the context of a hybrid metric Palatini gravity, and then I'm going to show you some different solutions that we found. Most of them numerical solutions, but a couple of them that we managed to find that are analytical solutions. So the motivation for modified gravity, I think you are all very aware of this. So we have an imbalance in the things we know. We have a late time acceleration, and when physics is faced with such an imbalance, either we add a previously unaccounted source, like for instance the the lambda term that has some problems itself, as you know, the fine tuning problem, etc. Or we change the governing equations, so the Einstein field equations. In here, in changing the governing equations, we are some people say limited by the Lovelock's theorem. I'd like to think of Lovelock's theorem as a guide to how can we improve or change the governing equations. Uh, so this part is looking for an action with more general curvature invariants. Some of them are successful in accounting for late time acceleration without invoking dark energy, and they have some success in explaining large scale dynamics of self gravitating systems without invoking dark matter. So the hybrid metric Palatine, we know that both metric and Palatine formalisms are successful in reproducing acceleration rate of the universe, but they are somehow flawed because they change the solar system dynamics, and the solar system is a scale where general relativity is well studied. Probably it's the only place where it's well studied. So a new approach was proposed, the hybrid metric Palatini. Here the action of the theory, in which you have the Ricci scalar, and we have a function of something that I will call the Palatini scalar. This Palatini term is constructed in terms of an independent connection, so it's not metric compatible. This will be the connection to a different metric that is conformally related to the metric that gives this Ricci scalar here. So this has been successful. This hybrid metric Palatini approach has been successful not only because it generated long range forces, so it passes the solar system tests, but it also allows for a scalar tensor representation, which greatly simplifies the analysis. So this is the scalar tensor representation, in which we have a part of the dynamics. We also have a potential here of the field, and then we have a coupling term here to the Ricci scalar that is one plus the scalar field. So you may look at this and see something very similar to the Brans-Dicke theory, with a minus 3/2 of the Brans-Dicke term, but there is a significant difference because of this um, of this term here that makes it different. So when we perform the variations of this action with respect to the metric and the scalar field, we get these equations. So here we force the appearance of the Einstein tensor, and then we have also here a modified or an effective Klein-Gordon equation for the scalar field. This is an important difference between the hybrid metric Palatini case and the purely Palatini case. In the purely Palatini case, the scalar field is not dynamic. In this case, as you can see from this part of the equation, is dynamic, and so it avoids some microscopic instabilities that Palatini models with infrared corrections have. So what about cosmic strings? Cosmic strings are topological defects that are formed at phase transitions that occur after spontaneous symmetry breaking. They are a feature of several grand unified scenarios that happen right after the inflation. Actually, the inflation is very important to the survivability of topological defects, because if these defects are formed too early, they become absolutely diluted in the accelerated expansion. But if they are formed too late after the inflation, then they'll dominate the dynamics of the universe. These topological defects may be of different types. We can have walls, we can have monopoles, and of course cosmic strings. That will depend on the minimum manifold of the potential. They have possible impact on CMB anisotropies, small scale structure formation, etc. They are the energy density of the strings is constrained by present cosmic microwave background observations. Is constrained also by lensing, and hopefully it will be constrained by LISA when it comes online eventually, because strings have a particular thing that they have magnetic flux inside of them. So that means they have to be either infinite or they have to be in closed loops. And when they are in closed loops, they will shrink these loops and they will emit gravitational waves, and that will give rise to a stochastic gravitational wave background that we can't yet detect, but hopefully in the future we'll be able to do so, and that will put some more constraints in the cosmic strings. So for this work, we consider a straight infinite cosmic string, with this energy momentum tensor. This is the Vilenkin's prescription for this, where sigma is the density, the linear density of the string. This is not totally general, since we ignore uh, pressure. There are some components of pressure in the direction perpendicular to the string direction. And then we consider a cylindrical symmetric static metric of this type, where k, u, and w are functions of r alone. If we impose now the energy conservation equations, and then the boost invariance in the t and z directions, the only surviving term of this will be this w square here. And so this is the analysis. So this is what we have here. If we impose the energy condition, we get this situation here, and then boost invariance to get u equals to 0. Then we do a rescaling, as you can see here. So r will become beta, and then this psi here. Beta will be a distance scale that will be set by physical considerations. And then we have these three equations. This one permits for us to find the field, the value of the field as a function of the radius. This one allows us to see the behavior of the of W, and then this one allows us to see the density, the linear density of the string. Another important characteristic is the mass of the string, the total mass of the string per unit length. So the first case that I want to talk to you about is the case of a constant potential. Now we need to define a potential, and then see where that leads us. So considering a constant potential, we can see that the field is monotonical decreasing at large values for the radius, so it decreases, but at very center of the string, the behavior is dependent on the initial conditions. So we have to set initial conditions for the field and for the derivative of the field. So we have here a small area closer to the center of the string, when it can be either almost constant, the scalar field, or it can even increase a bit, and then tends to zero at very large values of psi, or the radius. The metric tensor component, the only surviving metric tensor component, its behavior is almost independent of initial conditions till almost between 0 and 1 of the value of the psi, and then it changes at larger psi. As you can see, it will get a singularity, so it will become infinite at very large size. We will go back to that in a while. Just so a small note that in this case, and in most of the cases that we found, W at the center of the string, so at the axis of the string, so at 0, is not well defined. So we don't have W0 equals to 0. That would mean that we have an axis, so the axis is not well defined. And now, regarding the energy density of the string, we can see that it is decreasing, but it's, as you can see, very dependent on the initial conditions. So the form of the function is the same, but its value is very dependent on initial conditions. If if we impose the condition that we want the string density to be positive defined, this will take us to strong constraints on the scalar field and also on the derivative of the scalar field at the point zero, so our initial conditions. So the following potential that we use is this one, where lambda is positive defined. This kind of potential arises somewhat naturally in for instance in effective Kaluza-Klein theories from the compactification of higher dimensions. As you can see, it has a similar behavior as the constant potential for the field, uh, and also for the metric tensor component. But if we look the the string density, the string energy density, we can see that it's very different from the behavior of a constant potential. You can see here that it decreases to a critical value of psi, and then it reaches a singularity at finite psi. The last one I will show you, the last potential I will show you, it's the Higgs type potential. So the Higgs type potential we have here to that mu and that nu that appear here there in the potential. So the mu is related to the mass of the scalar field particle, while the nu is the Higgs self-coupling constant. Here in this work we consider it to be 1/8. That's approximately the the experimental value that we get. As you can see, the behavior of the scalar field is quite different from the previous cases. Um, they have an oscillatory type behavior, also very dependent on initial conditions. Uh, Also, the metric tensor component is also exhibit the same oscillatory behavior, but they are off phase one in relation to the other. So when the metric tensor component reaches a maximum, the scalar field is in a minima. And then for the string tension, also the same behavior in phase with a scalar field. This has important and interesting consequences, since none of these vanish or reaches a singularity in a limit in a finite value of psi. So for the conclusions, so this type of strings are inconsistent in Brans-Dicke theory, except if we allow for a lambda term, so a cosmological constant term. But here we could find solutions in the hybrid metric Palatini case. In all the considered solutions, we can't define an axis, so the value of the metric tensor at zero is not zero, and we can see that the behavior is strongly dependent on the value of the field and on the first derivative of the field at the axis of the strings. With the Higgs potential, string tension does not vanish, neither does the scalar field. Uh, for the potential equals to zero, and this particular form of the potential, we have found analytical solutions. So if you want to have a closer look, I'll upload this slides to the Indico page, so you can have the link for the work. Um, but we still have to study some more general type of string configurations. So, for instance, loops. We also need to consider the the strings with the pressure in the direction, not the direction of the string, but in the transverse directions, and then also, for instance, superconducting strings. So thank you very much. I'll stop sharing now.
Great, thanks. We have time for one quick question, please. Any questions? Okay, if no further questions, let's thank the speaker again. Our next speaker is going to be Yu Cheng Du. His topic is going to be gravitational wave in space-time with extra dimensions. Please share your screen and take it away.
Hello, everyone. Share my screen. So you can see my screen, right?
Yes.
Okay, thanks. So I'll start. So today I will talk about the gravitational waves in space-time with extra compact dimensions. So here's the outline. So first, I will explain the motivation of having extra dimensions and also why we want them to be compact. And then we go through several steps to compute the metric perturbation, the luminosity, and then finally to get the phase of the waveform and compare that with the experiment's result. And then I will do some analysis and give a summary. So first, why do we want extra dimensions? It could be a desire for unification. For example, Kaluza-Klein theory want to unify 4D gravity and Maxwell field. And it could be a requirement from the theory itself. We know that string theory requires different string theories require different number of dimensions. And also, the extra dimensions could provide solutions for a hierarchy problem. And I won't go into detail there because I want to save some time for the rest of the slides. So why do we want them to be compact? The first is due to our daily experience. So first, we only feel 3 dimensions, right? If there's extra dimensions, why we don't see them? So we think probably there is no large extra dimensions. And also, if the compact dimension is the extra dimension is compact and small enough, then we can explain why we don't see them. For example, if we think of a long 2-dimensional tube, when we are far away from it, it just looks like a 1D line. And the other reason is from the inverse power law of gravity. We know that in d space-time, if all dimensions are non-compact, think about Gaussian theorem, we know that the potential will depend on the number of dimensions. Obviously, we will have a problem if d is not equal to 4, does not equal to 4. However, if all the extra dimensions are compact, the problem is solved. Actually, we can calculate the potential by using the method of images, and this will be utilized. This method of images will be utilized through our calculation. So the contribution from the source in the compact case is equivalent to the contribution from the source and its images in the non-compact case. So for example, in d equals to 5, if we want to compute the potential, actually we just summing up the contributions from the sources and images, an infinite number of images. And when r, the distance, is much, much larger than the length of the extra dimension, actually we could, for a quick check, we can just simply replace this sum with the integral, and we could see that it does have the correct dependence of r. The leading order is 1 over r. So that's the reason why we want the extra dimensions to be compact. So here is our model, our toy model, which is the simplest case, where we have 4 plus n dimensional spacetime with 4 non-compact dimensions and n compact dimensions. They are all compact to small circles. And we all live on this 3+1 brane, which is marked with a blue line. And our binary source is also there, localized on this brane. Our logic is very easy. We want to compute the gravitational wave from the binary source.
So we're starting from the matter distribution, the energy momentum tensor. We compute the metric perturbation, and from the perturbation, we get the luminosity and calculate the gravitational phase of the waveform. So to get the metric perturbation, we basically solve the Einstein's equation. And we will use the relaxed Einstein's equation, which is actually exactly the same as the original one. It's just we write it in the other form. And the physical meaning is quite obvious that the perturbation at the location of the observer receives contribution not only from the matter, but also receives contribution from the gravitational field generated by the matter source. And this D'Alembert is the one in the flat background. And we will encounter 3 issues before we get our result. The first issue is about quadruple formula. So to solve this equation, we know that of course, we could use direct integration, just to use the Green's function and do the integral. But in ordinary GR, we don't do that. What we do is we utilize the quadruple formula to simplify the calculation. The advantage is we no longer need the small tij. We only need the information of this big, the matter energy momentum tensor and actually the 0,0 component information. However, in the case of the compact dimension, the quadruple formula fails. The reason is in this transformation, actually we do integration parts. There are certain terms we dropped because of the boundary condition. But now, since the extra dimension is compact, those terms are not 0 anymore. So the first issue is that the quadruple formula, we cannot use the quadruple formula, at least for the 5-5 component, and we have to do direct integration. The second problem is how to handle the Green's function. Look at this 5D Green's function. It's not quite friendly. If we directly use that, not only it makes the contribution hard, it's also difficult to generalize to general D-dimensional case. So the trick we use here is, to go back to momentum space, because in momentum space, the Green's function only have one form. And this is all this Green's function actually are the Green's function for non-compact case. For compact case, we just summing up, use the method of images, which is summing up the contribution from the source and all the images. And in the momentum space, it has this form. And look at this form and think of it in a 4D perspective. And we could think this 2 pi n over L is just kind of like mass, right? So if we treat this as a mass term, so we could say this part describes the propagation of a massive scalar. So basically, we are saying this 5D compact Green's function receives contribution from one massless mode and a bunch of massive modes. And the mass is this. And then even without explicit calculation, we would expect the something like Yukawa potential in our final result, right? That's the consequence of having a massive mode. And that is exactly true. And I don't want to go into detail of this thing, but the key point is here. This is the contribution from the massive modes. This is the contribution from the massless mode. We can see the massive mode does always have this exponential suppression term, which is basically the Yukawa potential. And this R is the distance between the observer and the source, and the L is the length of the extra dimension. So if we put in the typical number, you will see that this number is ridiculously small. So the conclusion is quite simple, and even, I would say, a little bit trivial, that the conclusion is the compact Green's function, through this analysis, we can safely replace it with 4D Green's function over the length of the extra dimension. And the generalization to a D-dimensional case is quite straightforward. You just replace this L by the volume of the extra dimensions. And that volume, this actual factor, 1 over the volume of extra dimensions, will combine with the gravity constant, D-dimensional gravity constant G, GD actually to produce a 4D gravity constant. And that is where the third issue will appear. So starting from the gravity constant, the d-dimensional case, we can generate a 4D gravity constant. It's very tempting to think this is just the Newton's constant, but actually it's not. The Newton's constant can be extracted from the G00 component, and through the calculation, we could actually see there's a relation between this Newton's constant and the G we defined by using the d-dimensional gravity constant. When d equals to 5, there is a difference of 4/3, and actually there is a physical meaning of this factor, and I will talk about later, this 4/3. And the Newton's constant, of course, will be measured by experiment. So after solving these three issues, we can't use the quadruple formula. Issue 2 is that we have to handle the Green's function. And third one, correctly identify the gravity constant. And finally, we can get our result. So in 5D, this is the result, the part coming from the big T and the part from the small t. And the key point is that the G is not Newton's constant, and the 5 component is non-zero. And here is the summary of the result of the metric perturbation. And we can compare the d-dimensional result with the 4D result. We can see there's an overall factor and a bunch of non-zero extra component. So from here, from the metric perturbation, then we use the gravitational energy momentum tensor to calculate the radiation power, and which is the luminosity. And here's the result. That we can see there is a difference between d-dimensional case and 4-dimensional case. And to check with the experiment result, go one step further, and we will compute the gravitational wave phase from the luminosity. And this is the 4D result. This is the 5D result. And there's a difference of 26%. And for the d-dimensional case, you can see that it depends on the number of dimensions, but it only becomes larger. So that is our main result. And a little bit of analysis. So we can analyze that in field theory. So we will see that we can see that our result does not depend on the extra coordinate. That means actually we are considering a 5D Einstein-Hilbert action and do the Kaluza-Klein reduction. And when we add in the matter source, we could see there is a coupling, a specific coupling between the matter and dilaton. And on the other hand, if we consider a general for the Einstein-Maxwell dilaton action, this coupling can be arbitrary. So we can say our model to the order we are considering is basically a special case of this for the Einstein-Maxwell dilaton case. And from the point of view of field theory, the matter will also interact with each other by exchanging the dilaton. So we can define the scalar charge and compute the potential energy between matter. And we plug in our special numbers, and then we see that why the gravity constant does not equal to the Newton's constant. That's exactly because the part, that's the fifth force, which is say matter also interact with each other by exchanging dilaton. So this is the familiar 4/3 factor. And also, just for our toy model, actually, we can also rule out the class of our toy model by considering just the solar system test. By Shapiro time delay, actually, if we compute the gamma parametrized post-Newtonian parameter gamma, and we will see that it's equal to a half in the 5D. And in general d-dimensional case, it gets even smaller. So the gravitational wave and also this solar system test produce two different ways to rule out the class of our toy model. So here is my summary. So the compact dimension, extra dimensions case will significantly change 4D GR predictions, and the difference is at least 26%. And as the number of extra dimension increases, the discrepancy will only become larger. And also solar system tests such as Shapiro time delay also rule out this class of models. We only consider these models as a toy model, as a baby step towards a more realistic model, which is the Randall-Sandra model we'll consider as our next step. The Randall-Sandra model is more realistic because the geometry is self-explanatory, and it has some interesting property, and more importantly, it passed the Shapiro time delay test. So it would be very interesting to see what would be the result of the gravitational wave calculation. So that is my talk. Thank you.
Thank you. Thanks for saving some time. We have 7 minutes for questions. Please take your time and ask your questions. Any questions? All right. If no questions, let's thank the speaker again. And our next speaker is going to be Shenfeng Yan. And his topic is going to be about the primordial black holes and a stochastic gravitational wave in the sound speed resonance cosmology. And take it away.
Okay, thank you, Wentao. Can you see my screen?
Yes, but not the presentation yet.
Okay, so is that okay now?
Yes, great, thanks.
Okay, thank you. Okay, hello everyone. I'm Shenfeng Yan. It's my honor to give a talk about my recent research to you. The title of this talk is Primordial Black Holes and Stochastic Gravitational Waves in the Sound Speed Resonance Cosmology. And I worked with Professor Yifu Cai, Dr. Chen Chao, and Dr. Wang Bo from the University of Science and Technology of China, and Professor Chunshan Lin from Jagiellonian University, Poland, Dr. Xi Peng from Hong Kong UST, and Dr. Donggang Wang from Leiden University and Cambridge University. So this is my content of this talk. Firstly, I'll give a brief introduction to sound speed resonance mechanism. Then follow SSR mechanism. We can investigate the stochastic gravitational waves. We have finished 2 articles in this topic. One is the scalar induced gravitational waves background, and another one is the SSR of stochastic gravitational waves background. In the end is a summary. So let's go to the first part. It's SSR mechanism. So the first question is what is primordial black holes? Primordial black holes is a type of black holes which is formed through gravitational collapse of primordial overdense perturbations, which is very different from the common black holes formed by the collapse of dying stars. It is firstly proposed by Zildovich, Hawking, and Bernard Carr in the 1970s. Let's have a look at some properties of PBH. The picture in the left-hand side shows the formation of primordial black holes is much earlier than other astrophysical black holes. In this period, some modes of primordial fluctuations during inflation re-enter the Hubble radius. Some of them are potential to produce the overdensity collapse into the primordial black holes. And the PBH has a lot of cosmological and astrophysical implications. At first, it has analogy dynamics with cold dark matter. And for the mass of common PBH, they might be gravitational wave sources. Then small PBH may evaporate in a dramatic way. It may leave us gamma ray background, and astrophysically, PBH also might be the source of gravitational lensing or supermassive black hole seeds. So the second question is also important. That is, how did PBH fall? As I just mentioned, once the overdense perturbation re-enter Hubble radius, it may gravitationally collapse into black holes, and the mass of the gravitational of the primordial black holes is really large. If at the 1 second after Big Bang, the mass of the primordial black hole could be a 10 to 5 solar mass. So how to enhance primordial primordial perturbations? It's a question for all the early universe models. So from the effective perspective, the primordial curvature perturbations is in this form. It is proportional to the inverse of sun speed cs and the slower parameters. So in some mechanisms, the perturbation was amplified by separating sun speed cs and slower parameter epsilon. So we proposed a more efficient way to amplify the perturbation via parametric resonance effect. That is a sun speed resonance mechanism. This is a basic equation for the parametric resonance, which is also the equation of motion in preheating phase. Near the K star, near the scale K star, the mode grows exponentially in this way, and while the modes away from K star are unaffected. Here, the blue curved line shows the evolution of K star and mode in the theta approximation. It's enhanced by this mechanism. The green line is this analytical result. The orange line is a mode which is not relative to the mode of K star, so there is no resonance. The dashed green line is the Star-Robinsky inflation model, and that fits the BS approximation result very well. So this picture, in this slide, the picture shows the power spectrum. In fact, there are multiple very narrow resonance peaks, but only the first peak is dominant. So we use a delta function to approximate this spectrum in later simulations. In the meanwhile, K star must be small enough to avoid affecting the CMB region. Okay, so the results proves that the SSI is really efficient. It's really easy to enhance the abundance of primordial black holes to a very high level. Here, the FPBH is a PBH shear to total energy density of the universe. The dashed red narrow peaks corresponds to the different choice of resonance frequency K star. The yellow solid curve that mainly depends on the amplitude parameter C. Okay, that's a brief introduction to the sound speed randomness mechanism. So the second part is scalar-induced gravitational wave background. So once we have a peak of primordial density perturbations in the power spectrum, from the couplings of a curvature perturbation itself, or to the other perturbations, and the enhanced primordial perturbations could induce the two kind of things. One is the PBH. I just gave an introduction in last section, and the second one is the secondary via secondary couplings to produce the induced gravitational waves, and they are all cause correlation to the primordial curvature perturbation. So in our work, we investigate the induced gravitational waves from three stages from the SSR mechanism, but which is from the sub-Hubble region during inflation, and the super-Hubble region during inflation, and the third one is as usual, it is to investigate the induced gravitational waves produced in the radiation domination. But only the gravitational waves produced during radiation domination and the sub-Hubble region dominates in our results. This is our result. The two upper panels shows the abundance of the primordial black holes, and the lower panels shows the result of the induced gravitational waves. The red line is in the spectrum of the gravitational waves from produced during inflation, and the purple line is the spectrum produced in radiation domination, and the dotted line is the profile of the spectrum, because in the detections, the sensitive signal is the profile of this figure. So that's figure is we have two peaks in the power spectrum if the SSR induced gravitational waves can be detected. Okay, the third part of my talk is the SSR of stochastic gravitational wave background. So we know that gravitational wave events GW170817 provide us a tight constraint on gravitational waves propagating speed like this. But actually, such events happen in low redshift universe, almost lower than 1. So question would be asked is how about the gravitational wave speed in very early universe? In standard paradigm, gravitational wave speed equals to the speed of light. But if this is a deviation from speed of light, we believe that it is promising to reveal some new physics beyond stand models. This is a natural process for us to achieve oscillation, so-called reheating or preheating. Once the scalar rolls down to the minima of the potential after inflation, the field starts to oscillate. Owing to the phi dependence of gravitational wave speed, the gravitational wave speed start to oscillate too. But due to the expansion of the universe, the oscillation will be diluted. That's the origin idea of such parameterization in this work. And in the very late universe, gravitational wave speed reduces to unity, which satisfy LIGO and Virgo's observations. So now, once we have the oscillatory speed of gravitational waves, let's go to the model calculations. The general equation of motion of tensor modes is this one. But if we focus on the subharbor modes, friction term can be omitted. Thus, we got a Matthew-like equation, but this equation dominates for just a brief period. After that, the friction term becomes dominant. So after the analyze of this our ideas, let's turn to the full exact physics of the model evolutions. The purple line is the evolution of upper panel, the two upper panel figures. And the purple line is evolution of modes with oscillating gravitational wave speed, and the orange curve denotes trivial tensor perturbations. The upper panel is the mode function evolution along conformal time. We can see the mode function decays owing to the expansion of the universe. In the equation, that is the friction term of that equation. And the lower panel shows the spectrum at the end of radiation domination. There is a bump on the spectrum. It's a figure of our results. And this page shows the gravitational wave background spectrum. Sorry. And this page shows the gravitational wave background spectrum versus to the experimental noise and the signal to noise ratio distribution control for LISA, ET, and C from left to right. And thus the current and the future experiments can make constraints on our mechanism. So in the end, it's the current progress of SSR mechanism. We have finished more than 6 works in this topic, and we will investigate it more in the future to see some interesting mechanism or some interesting implications in this SSR mechanism. So that's a summary. Sun-speed resonance is a very efficient mechanism to produce primordial black holes. Primordial black holes formation can induce second gravitational waves, provide multi-messenger detections for PBH, and the constraints on sun-speed mechanism. And the SSR of gravitational waves opens a new window for testing new physics at very early universe. And how to achieve SSR mechanism of gravitational waves once we consider the progress during inflation is left a question for the further investigations. So thank you all for your lesson.
Thank you. Thank you for the control of time. Any questions? No questions?
Okay, thank you.
Okay, no questions. Please stop sharing. And our next speaker is Ana Ribeiro. Ana, are you there?
Hello, good morning.
Good morning. Can you start sharing your screen?
Yes, just a moment.
Perfect.
Okay.
Please take it away.
Okay. So hello, everyone. Thanks for the opportunity of being here. I'm here actually to present part of my results for my master thesis, which I concluded this year in March, actually. This thesis was done under the supervision of researchers Daniel Vernieri and Francisco Lobo, and we wrote a paper recently, which is available in archive, and hopefully it will be published soon in a physical review, which contains most of the results from my master thesis. And of course, it's concerned with effective F/R actions for modified loop quantum cosmology models. So in this paper, we are concerned with the initial singularity problem of the Big Bang model, which, as you know, it's basically the fact that in the beginning of the universe began with infinite density, because since it's expanding, it must have been just a single point, meaning with infinite density, and we call it the initial singularity problem. And moreover, we expect that a quantum theory of gravity is needed to understand better the beginning of the universe. One such theory, one possible theory we have today is loop quantum gravity, as you know. And this full theory has a reduced model, loop quantum cosmology, that yields this equation for the evolution of the universe. We can easily identify this equation as being the Friedman equation with a modified source. And moreover, we can see that this equation states that the universe can only reach a maximum density, which is finite. We call it the critical density. And moreover, this equation shows that the universe behaves in a cyclic way, so going from contraction to expansion through a quantum bounce at this critical density. Here, the main idea I'd like to leave is that in the context of loop quantum gravity, the way we get this equation is through an Hamiltonian description. So we start with an Hamiltonian constraint. And the main idea I'd like to leave here is that this constraint contains two important terms, the Euclidean and Lorentzian. And in the full theory, these are treated separately and then they are quantized. But in this reduced model, loop quantum cosmology, they are actually treated as proportional to each other. So they are treated in the same way. Having said that, since by doing this, we are departing from the full theory, there have been many attempts into incorporating more aspects from the full theory into this sector of loop quantum cosmology. And yet there's still no systematic way of doing this. As such, in our paper, we consider two modifications of loop quantum cosmology, so 1 and 2. And in each of them, these terms are treated separately. Thiemann's regularization is used in both of them. And additionally, for the second model, there's also the use of this relation between the extrinsic curvature that appears in this term and this that's related with the field strength that appears in the other term. So naturally, by doing these different treatments, we arrive at different Friedman equation, if you want to call them Friedman equation. And you can already see that they are more complex compared to standard loop quantum cosmology. And moreover, for the first model, we actually have two branches of solutions. So one for before the bounce and the other for after the bounce. So we say that the evolution of the universe is asymmetric with respect to the bounce for the first model. For the second model, it's again symmetric as well as in standard quantum cosmology. And here, for the first model, I'd just like to point out that the second branch, the B plus branch, poses phenomenological problems if it is to describe the universe we live in today, because this constant alpha is interpreted as a modified Newtonian constant, and this rho lambda is identified as, just a moment, this constant rho lambda is identified as an emergent cosmological constant. So changing the subject a bit now, we know that we can derive the Einstein field equations through using an effective an action, which is called the Einstein-Hilbert action. Just to recall, this is the Einstein-Hilbert action. We start from here, we make a variation with respect to the metric tensor, and then we arrive at the Einstein field equations. And moreover, the usual Friedmann equation in GR is calculated by assuming the Friedmann-Lemaitre-Robertson-Walker metric and a perfect fluid description. And in our case, in our paper, we are also considering a flat universe with a zero cosmological constant. And then we arrive at the usual Friedmann equation. So why am I saying this? It is because the question of our paper is basically, is it possible to do the same for these equations that come from loop quantum cosmology? So can we derive them starting from an effective action? And you will see why I call it effective. And this is the question we are addressing. So if the action, it cannot be the Einstein-Hilbert action, of course, so we need to change the actions. And we did so that's from GR by a general function of f of r. You can hear me well, right? My connection is unstable, apparently.
A little bit choppy, but it's okay now. Please go ahead.
It's okay.
Yep.
Let me just check one thing, 1 second. I believe it's okay. I think now it's better. Okay, so moving on. So we have changed the Lagrangian from the Einstein-Hilbert action by using metric f of r gravity. And so if we do the same, if we make the variation with respect to the metric tensor, we get the corresponding field equations. And here the important message is that they are now fourth order equations instead of second order field equations. And now the question is what we do about this, because the only theory we know of gravity is a second order equation, leads to second order field equations. So we can either say that our theory is really a higher order one, or we can treat it as an effective one by reducing its order, which was what we did. So we used the covariant order reduction technique, which takes the full equations from f of r and reduces their order. And in this case, these equations are only valid when the deviation, which we denote by this term, I didn't mention here, that we are parameterizing f of r as the Lagrangian from GR and a deviation term, phi of r. And so this deviation must be much smaller, of course, now in these reduced equations than the Lagrangian from GR. And in practice, what we did is setting epsilon to 0 by removing these additional higher order terms. And then with that equation, you write the reduced Ricci scalar and tensor, and then you substitute those reduced expressions back in the terms of higher order, and thus you get these equations. And these equations give solutions that are perturbatively close to the ones we find in GR as well. And so we can do the same. We can assume these two conditions and determine what we can also call a modified Friedmann equation, but in the context of f of r, where we have here this function phi of r, which we don't know yet. That's what we want to determine. You will see how. So actually in our paper, we were interested in extending a previous analysis done in another paper where a massless scalar field was assumed. And with this procedure, the covariant order reduction, an effective action was found that leads to the equation of standard loop quantum cosmology. And of course, this is again valid only for an interval of values of R or density. So in our paper, again, we have a reduced Friedmann equation from f of r, and we have the Friedmann equations from loop quantum cosmology. And now our goal is to make them the same. So you can write all of these in this general way, and then we will want them to be the same. Moreover, this basically means we need to solve this differential equation by substituting phi of r depending on the model, and then solving for phi of r. And by doing this, you get the function f of r, meaning you get an effective f of r action that leads to that specific bounds. In our case, again, we are using assuming massless scalar field, which further simplifies the differential equation. And now to our results. So this is again what I was explaining. Here is just to mention that we used Wolfram Mathematica to solve these equations, because remember, these are very complicated expressions. And then we substitute phi of r using the relation between r and the density, and then solve for phi of r. So the results are here. For the first model, first branch, this is the solution we have obtained, where we have identified here what are called hypergeometric functions. So this is for the second branch, and now for the second model. And now, because these are so we cannot tell much by just looking at the solutions, as such, we computed Taylor expansions of all of them. Again, you can see here that the second branch of the first model is a little bit different from the other two. We have here a constant. We also have a coefficient for r that's not 1 compared to the other ones. I recall that this is the branch with phenomenological problems. And now this is the easiest way to visualize our solutions by looking at plots. We have plots for the deviation only and plots for the full Lagrangian. If you want to see, I can show in the question part plots just containing, for instance, loop quantum cosmology or this branch, and so on, loop quantum cosmology and the other options. So, but here there are all the solutions. And now I'll move on to the conclusions by starting commenting on the fact that the two derivatives are positive. So the first one being positive allows for a positive effective gravitational coupling constant, because in f of r, we can write the field equations in this way. And here we can identify this effective gravitational coupling constant, which then depends on this first derivative. If this first derivative is positive, then this constant is positive. And by being positive, we are avoiding the ghost behavior of the graviton. The second derivative, being positive, avoids this instability, the Dolgov-Kawasaki instability, which then is also related to avoiding ghost behavior. Now, here, using the Gauss-Bonnet theorem, we can also say that, well, we have found solutions of this form, but the Gauss-Bonnet theorem tells us that these two Lagrangians, there are not only two, these are a list of Lagrangians. They are related by this constraint and they lead to the same equation. So we have found a family of Lagrangians for at least these two cases, which lead to the same field equations, to the same loop quantum cosmology equations, I mean. And then finally, I'd like to restate that our approach, since it's an effective approach, is only valid for when this condition applies, meaning it unfortunately doesn't work when the densities are very high, which are the major, the regions of high interest, let's say, close to the bounds. But even so, we claim that our Lagrangians effectively describe the universe after and before the bounds, even though at the bounds there's this issue. Thank you for your attention. Any questions?
Yeah, time for questions. Any questions for Anna? So if no questions, let's move on. I think we can end this session earlier than they planned. Thanks again.
Thank you.
Our next speaker is David Benesty. Can you share your screen, please?
Let me see if I can put like a full screen.
Yep.
Okay, so now I need to share like the full screen. Yes. So everybody see it?
Yes. Great.
Okay. Okay, so I may start. Thanks.
Yep.
So my name is David Benisti. I'm now a visitor and a postdoc in the Ben-Gurion University and a visitor in Frankfurt Institute for Advanced Studies. And soon I will begin on October my fellowship at the University of Cambridge. So during my PhD studies, I was also like a visiting researcher in Frankfurt Institute, and we had a collaboration that related to the subject of covariant canonical gauge theories of gravity. So in principle, what I'm going to present today, this is based on the work of Jürgen Struckmeyer and David Vazak. They are written here. I mean, they invented like the original formulation, but with my work, we extended part from this idea to gravity, to extended theories of gravity. But what I want you to keep in mind today that it is possible to write down Hamiltonian or covariant Hamiltonian, or we'll explain what do I mean by covariant Hamiltonian, to Einstein theory of gravity and also for the other quadratic theories of gravity. So the motivation for this kind of formulation is how to construct these theories from the basic principles. So as we all know, it is possible to separate the space-time into two different components. So we have one component which is the metric, and we have another component which is the connection. So the connection itself is like more, let's say, geometrical parameter that can help to transfer like one vector to another vector, like in the same space-time. So to do like one transformation from one to another. Now, as we know, the connection itself can be separated to three different components. I mean, there are more, but these are the three that exist like in our community. So the first one and the most important one, this is the Levi-Civita connection, which is related, I mean, if we have like the metricity condition. The second one, this is like the torsion contribution, or in this case, the contorsion contribution. So if there is like some anti-symmetric part of the connection, which is actually a tensor. And the last part, this is some non-metricity term. So in my case today, I mean, it is possible to extend also with torsion and also with non-metricity. I'm going to focus only on the Levi-Civita connection. So there are two formulations in general theory of relativity. Before I'm going to show the formulation, I'm going to show the correspondence which related to the metric and the metric affine formalism, the Palatini formalism. And then based on this kind of connection, this kind of correspondence, I will build like I will construct the gauge theory. So there are two formulations, basic formulations in general theory of relativity, and this is the metric formalism and the Palatini formalism. And the differences in between them, that in the metric formalism, you only do the variation with respect to the metric. And this is why, for instance, like in f of gravity, as you saw, you get like higher derivatives. However, in the Palatini formulation, you have two different variations. You have the variation with respect to the connection and the variation with respect to the metric. And there are two independent fields. Okay, there are two independent variations that you have to do. And for instance, if you have like r plus alpha r squared gravity, you get a different results. I mean, if you have Einstein gravity, there is no difference in between them. But if you have any small modification beyond Einstein, completely different physics for the whole different formulations. So the question that we ask ourselves, I mean, based on the formulation of Jürgen and Vazak, we thought which kind of correspondence it's possible to build in between these formulations. So before I will show you, I mean, the result, you can see, I mean, the differences in between the metric formalism and the metric affine formalism. So these are like the field equations, so the variation with respect to g mu nu for r squared gravity, r mu nu gravity, and quadratic Riemann term. So as you can see, you have like some tracelessness contribution for the whole quadratic theories, but you have some higher derivatives term. Now, as you can see, if you're searching like the same corresponding field equations, but in the Palatini formulation, you have only the tracelessness part, and the second variation gives you like another condition on the curvature inside. So the differences in between this formulation, this is like the higher derivatives term that does not appear in the metric formalism, but that does not appear in the Palatini formulation, but appears in the metric formulation. So how it's possible, for instance, to begin with Palatini formulation and to finish with metric formalism? So I mean, this term, I will interpret it in a few seconds, but this term was invented by Struckmeyer, actually can take any action that you write down in the metric affine formulation. So it means that you have 2 degrees of freedom, you have the connection and the metric. And when you add this term, immediately you get second order formalism. And I will explain how. Because this term actually acts as a Lagrange multiplier. So as you can see, this is like a tensor, k alpha beta gamma. It's multiplied by the covariant derivative of the metric. Now, in the first order formalism, the covariant derivative of the metric is not 0. You need to get it as a result. So you have like 2 different variations. So we have bottom of line 3 different variations, because we have the variation with respect to the metric, the variation with respect to the gamma, the connection, and the variation with respect to k. Now, from the variation with respect to k, we get the metricity constraint. So we get g alpha beta comma gamma equals 0, which gives us that the connection equals to Levi-Civita connection. Afterwards, we have the variation with respect to the connection. So we get some contribution from the metric, and we get some contribution for this k term. So as you can see, this is the contribution for this k term. And afterwards, we have the variation with respect to the metric. So, okay, let's say that I put like some action and I added like this term. How can I finish with the second order formulation? So bottom of line, because of the contribution of this additional term, and you need to play with it a bit, I mean, to do like some different indices contribution, eventually it's possible to show that the missing terms that you have seen, like the red missing terms, are actually will come from the derivative of this k term. So let me show you an example to really emphasize what do I mean. So as you can see, these are the variations with respect to the connection for the quadratic theories. Now, if we take like the corresponding equation that I'll show you, and I put inside like this variation, immediately I get the whole higher derivations of higher derivatives that you saw like in the actions. So bottom of line, the original term, which was like the tracelessness term, appears immediately because of the variation with respect to the metric in the Palatini formulation, in the first order formulation. But because of this k term, you get the contribution of the higher derivatives. Okay, any questions so far? Because now I'm going to switch for a slightly different idea that's based on this. Okay. So it is also possible to show that the same principle exists in the path integral approach. So if you have like an action that depends on the gamma and the metric, I mean on the connection and the metric, or as what's called the first order formalism, but you have like this additional Lagrange multiplier term. So this is actually acts like some Gaussian function that gives you like a delta function inside. Okay. So bottom of line, you end with only with the metric, and the gamma equals to the and the connection equals to the Levi-Civita connection. So eventually you have like the second order formalism. So what is the physical interpretation of this kind of term? I mean, of this kind of K multiple by G alpha beta comma gamma. And this is the main idea of the talk today. So it is possible to extend like this partial derivative to a covariant derivative. I mean, it was originally a covariant derivative. So the interpretation is the following. I mean, as you know, usually when I want to write down a Lagrangian or Hamiltonian, so the Lagrangian has like some derivatives term in the beginning. So it's going to be like PQ dot minus the Hamiltonian, which depends only on P and Q. This is like in general. However, the idea of Jürgen Struckmeyer and David Vazak was to extend this time derivative PQ dot to a covariant derivative, so four-dimensional derivative. So now in our case, as you can see, it's going to be like four-dimensional derivative with respect to the metric. So for instance, if my degree of freedom is going to, my parameter is going to be the metric, so the corresponding covariant momenta is going to be this K, okay? Because I'm taking like the four-dimensional derivative. So in the beginning, they started with partial derivative, okay? And they have like two different systems, but they wanted to do like the same thing also for the connection. So you have the metric, you have also like the covariant momenta of the metric, minus some covariant Hamiltonian. So you have in addition the connection and some covariant momenta of the connection itself. Now is the idea to gauge this kind of covariant Hamiltonian. So to extend like the partial derivative into a covariant derivative. Now, as you know, the connection is not a tensor. So you have to add some additional terms inside in order to have a covariant derivative. And the magic was that after they tried like to use like the minimal terms in order to address like what should be the corresponding covariant derivative, let's say. So they got the Riemann tensor. So bottom line, what you are seeing in front of your eyes. I mean, it's a very simple idea and very elegant idea. You have the metric, and you have its covariant momenta, this K tensor, and you have the connection and its covariant momenta Q. And afterwards, you only built like the Hamiltonian that based on these degrees of freedom, or K, or Q, or gamma, or G. That's all. So bottom of line, it's possible to build Einstein gravity. This is what I'm going to show in a second, from this kind of formalism, from this kind of Hamiltonian. So you have like a momenta and you have the degree of freedom, and you can build Einstein gravity. Now, I want to emphasize in addition that the connection itself is going to be the gauge field, because as you can see from the transformation of the connection in between two systems, it's possible to show this is actually very similar to a gauge field that has like a rotational and inhomogeneous part. So how we can we actually show that this kind of Lagrangian is similar to Einstein and quadratic theories of gravity? So before I'm going to show that, we need to keep in mind that we have 4 degrees of freedom, because we have the metric and we have the connection, and we have like the two corresponding covariant momenta. And these are only the variations. Okay, this is very simple to calculate. So let's sample some Hamiltonian. So the Hamiltonian that it's very reasonable to address, this is like a quadratic Hamiltonian. So we Q square minus some Q multiplied by a metric. So it's going to be like linear scalar of Q, and also like the Q square term. So I'm not going to show like the whole mathematics, but after you calculate the variation with respect to Q, it is possible to show that this covariant momenta of the Riemann tensor actually has this form. Now, as you know, this is like the difference in between the Riemann tensor and the Sitter tensor. I mean, this is like the Sitter space that's related to the metric contribution. And the difference in between them, this is like the Q tensor. So after a bit mathematics, I mean, okay, this is like some procedure that's possible to do. It is possible to show that, I mean, this Lagrangian that I show you, this Hamiltonian that I show you here, is actually corresponding to the same Lagrangian that I'm writing down here. So you get some cosmological constant that's related like to the original parameters of the Hamiltonian, and you get Einstein gravity from the linear Q term, and you get quadratic Riemann gravity from the quadratic Q terms. Okay, so if you derive all of the equation of motion, it's possible to show they actually converge to the same equation of motion. So what I want you to do, this is like to extend this idea. So because the Q is the corresponding momenta of R, of the gamma, yeah, so I define like the same Q scalars. So it's possible like where you have like the definitions for R mu nu, so this is going to be like multiple by some delta tensor, the Dirac delta. So, and also to define like the R scalar, like the Ricci scalar and the Ricci tensor. So in the same way, it's possible to define like the Q alpha beta and the Q scalar. So when you actually do that combination, so the most extensive Hamiltonian is going to be like, let's say some G0, some linear Q, and some quadratic Q tensors inside. Okay, and this is the Lagrangian that you saw before. Again, you have like the Legendre transformation, like the K multiple by G alpha beta comma gamma, and Q multiple by the covariant derivative of the gamma, let's say, I mean, with some additional terms, of course, because gamma is a tensor. So now, the same variation that I showed you before with respect to Q, it's not possible to do it, I mean, directly. So you have to do like the variation with respect to Q, and then you get like this kind of relation in between R and Q, but then you need to do like a trace twice and then to plug in the whole trace of the equations. Okay, so this is a bit messy, but afterwards, let me show the bottom of line result. So after doing the variation with respect to Q, it's possible to show that the Q is related to the Riemann tensor and the Ricci tensor, the Ricci scalar, by according to this kind of new coupling constants. And what is the bottom of line? After we plug in all of these kind of variations, it's possible to show that this Hamiltonian corresponds to this Lagrangian. Okay, so from the linear term of R, of Q, you get like the linear term of R, but you get also like all of the higher curvature gravities, so all of the higher curvature terms. But one thing which has to be mentioned, this is also that alpha 1 has to be exist. So because this is, I mean, the coupling to the quadratic Q term cannot be 0, as you can see. I mean, G23 cannot be 0 in these terms. So this is actually means that the quadratic Riemann term has to be essential, or you can take this as some limit of this kind of formulation if you want only Einstein gravity. In addition, what we get, this is some effective cosmological constant. So even you don't begin with a cosmological constant, let's say the G0 is 0, still you have some contribution from the couplings of the Hamiltonian, the original couplings of the Hamiltonian. Okay, so, and this kind of prediction for the cosmological constant had what's called the cosmological seesaw mechanism. So what do I mean by cosmological seesaw mechanism? Seesaw mechanism is something like that we use like in particle physics, why one particle has like a very low mass and the other one has like a very large masses. However, in this kind of formulation, it's possible to show that even one parameter is very large, the total parameter, the cosmological constant, has to be very low. Okay, so even like as long as G2 and G3 are going to be very, very large, lambda has to be very low. So this is kind of, let's say, some approach to the cosmological concept problem. Of course, not a solution. This is a more fundamental problem. Okay, now it's also possible to connect this to Gauss-Bonnet term or conformal theory of gravity. Now, so what I would love actually to mention before I'll finish, that this kind of formulation is very, very similar to coincident GR. So what is coincident GR? In this kind of paper, Lagina, Heisenberg, and Koivisto and others, they tried like to build the full formulation of GR using different parameters or different building blocks. So as long as you have this term is not a tensor, but you need to have this term in the action bottom of line, so you get GR. So it's possible to construct this term from teleparallel gravity or from gravity, so Q in the sense of non-metricity contributions. But in order to do that, they added some Lagrange multipliers that couples to the covariant derivative of the metric or that couples to R. Because, for instance, if you are in teleparallel gravity, 1 minute, thanks. Okay, I'm going to finish. So in teleparallel gravity, for instance, you need to set the R to 0 because you based only on the torsion, or in the non-metricity, you based everything on the G alpha beta comma gamma not equals to 0. So, but bottom of line, what I wanted to show that these kind of Lagrange multipliers are actually the same tensors that we used before. So I mean, this is the K tensor and this is the Q tensor, as you can see. So bottom of line, the two different formulations started from a different perspective, but ends with similar results. But our interpretation, this is actually can be written in covariant Hamiltonian form. So if to summary, with this K multiplied by Q, it is possible to connect like two formulations of GR to begin with the metric affine and to end with metric affine formulation. And it's possible to extend this to Hamiltonian covariant formulation. And also there are some implications for quantum gravity because we don't have higher derivatives in the action. Only one comment that it is possible to extend this also to vector fields and scalar fields and also to fermion fields, but this is the whole topic for a different time. Okay, that's all. Thank you very much.
Yep, thank you. And let's have one quick question. Any one quick question? Okay, if no questions, and please stop sharing, David, and thank you. Let's move to our next speaker, Moe Kukihara. Hello.
Hello.
Hi. Could you share your screen, please?
I'm ready.
Okay, good. Take it away, please.
Hello, everyone. Thank you for giving me this opportunity to talk here. I'm Moe Kukihara, a graduate student from Fukuoka University. Today, I'm going to talk about study titled Proving Multiverse Using Gravitational Wave Observations. The goal is to search for evidence of collision between universes predicted from the multiverse cosmology using the gravitational wave observations. Multiverse is the idea that there are many universes, not one. Here are two examples. The first, according to the inflation theory, which a part of the universe again rapidly expands and then small bubble universe is born. This procedure repeats again and again. After that, universe becomes multiverse. The second is the membrane universe. There are three-dimensional spaces, dimensional membranes of the universe that are different from each other, and many of these membranes are lined up. Gravitons are located in a ring and do not adhere the three-dimensional space. So only gravity works in both the inner and outer spaces of the membrane. Therefore, if there are other universes, it is possible that it will collide with our universe. There are some studies to verify whether this has been collision between the universes in the past. Some explored the temperature fluctuation that occur at the surface of the collision between the universes. This temperature fluctuation appears as a ring pattern on the cosmic microwave background radiation, which is investigated by WMAP observations. As a result, 4 sky areas were reported that are consistent with the ring pattern. However, it should be noted that since the universe is expanding, the effects of collision is diluting. In this research, we proposed for the first time a method to verify multiverse using gravitational wave observations, which is independent of the previous studies. From the theory of the multiverse cosmology, it is possible that our universe collides with other universes locally in its history, which may result in local changes of the curvature of the spacetime. Our method firstly makes triangles using two detected gravitational wave sources and the sun, and then measures the curvature of the triangles. From the WMAP curvature measurement, the curvature of the entire universe is said to be flat, in which case the sum of the internal angles of the triangle areas is 180 degrees. The curvature is negative when the sum of the internal angles is less than 180 degrees, and positive when the sum of the internal angles is greater than 180 degrees. This is the observation data of gravitational wave telescope LIGO and Virgo. We use these to look for the collision between the universes. To make a triangle area, we need to know the gravitational wave sources. For the purpose, the direction to the gravitational wave sources are important. This is a probability map of the direction to each gravitational wave sources. An island is the figure has a probability of existence of 90% or more. However, as you can see from the figure, the size of the island is wide, which means the error is large. Therefore, we try to find the point most likely to be on the island, and we used it as a source of gravitational waves. This figure shows the most probable sky position of gravitational wave detected from 2015 to 2017. Now let's talk about the procedure of how to calculate curvature of the triangles. 2 of the 11 gravitational wave sources were selected in order to create a triangle area with the sun. There are 55 combinations for all. We compared the observed value of the distance between the 2 gravitational wave sources and the model value, which assumed simple cosmological evolution. We calculated the curvature as follows. I will talk about the estimated distance between the 2 gravitational wave sources by gravitational wave observations using ZW150914 and ZW151012 as examples. We created a triangle like this using gravitational wave sources. Using the distance data in the table on the right, we estimated the distance between the two gravitational wave sources. So with this procedure, we obtained 55 distance in total. Next, I will talk about the estimated distance between two gravitational wave sources by the flat space model. Assuming the gravitational wave source is born in the early universe, we considered the distance between the two gravitational wave sources as the size of the universe at that time. Since a gravitational wave radiation with a redshift z occurs when the universe is 1/1 plus z times the current size, we calculated the model value as follows using this equation. Let's talk about the estimated model values using CW150914 and CW151012 as examples. First, if you read the value in the left sheet from the table on the right, the average Z is 0.15. Therefore, 1/1 plus Z is 0.87. This indicates that it was emitted when the size of the universe was 0.87 times the current size. Assuming the current size of the universe is 13.8 billion light years, the size of the universe at that time is 12 billion light years, or 3,679.2 megaparsec. We used these values as a model values, and with this procedure, we obtain 55 distance in total. The sky position of each triangle area like this. Given the error bars of the distance of the gravitational wave from the sun, the observed value and model values for all 55 sky areas are as follows. Blue dots show the distance between gravitational wave sources estimated by the gravitational wave observations with uncertainty. Red dots show the distance calculated using a simple model of the cosmological evolution. As a result of comparing observed values with the model values in each of the 55 sky areas, it is not possible to specify the curvature in the 12 sky areas because both signs are possible. But in the 43 sky areas, the results suggest a negative curvature. Here is summary of my talk. If there is a universe different from our universe and collision occurs between our universe and it can be said that the collision surface has a peculiar curvature. In order to find the peculiar curvature, we measured curvature of various triangles on the sky. We created 55 triangles using gravitational wave observations and investigated whether the curvature of each area was flat or not. In the 43 sky areas, the estimated distance by the space model was always larger than the estimated distance by the gravitational wave observations, so negative curvatures were suggested. This is affected by the simplification of the space model, and it is necessary to refine the model in the future by considering the effect given by other objects. On the other hand, Area 5, Area 14, 22, 29, 34, 35, 41, 42, 43, 44, 45, 55, in these 12 sky areas, the estimated value by the flat space model is included in the error bar of the estimated value by gravitational wave observations, and it is difficult to compare the distances. In the future, it will be important to reduce the error in order to limit the sign of the curvature. That is all for my presentation. Thank you for listening.
Thank you for your interesting talk. Any questions for Moe? No questions? Okay, if no questions, let's move to our last speaker for today, Kupatitiu Romero. Hello.
Hello, yes, morning.
Can you share your screen, please?
Yes. Can you see it?
Yep, yep. Thanks.
Okay.
Please take it away.
Yeah, the topic of the talk is inflationary supersymmetric FERLW quantum cosmology. This is a work done with a student, PhD student, Martinez Perez, and Professor Vázquez Báez from University of Puebla. Cosmology, as everybody knows, describes the general laws of the universe. And in general, we can do it by a classical formulation with good agreement with of observational bounds. However, the first stages of the very early universe are first expected quantum gravity phase, where there are quantum space-time fluctuations. Then after that should be a homogeneous phase, from which starts the inflationary phase, where there are inhomogeneous perturbations which originate the structure seeds. These inhomogeneities follow or can be described by as quantum fluctuations from a quantum field theory of metric perturbations in a homogeneous background. Then we have first quantum gravity, then this inflationary phase, where, however, the metric perturbations can be treated as by a quantum theory. This suggests to treat this whole epoch by a quantum theory of cosmology, quantum cosmology. Of course, classical physics follows from quantum theory. During the inflationary phase, very little is known. I mean about a model of physics, the physics of the universe. And it is, we can expect that supersymmetry can play a role there. Supersymmetry it gives a unified framework for bosons and fermions, improves the behavior of divergences, the divergences, the bosonic divergences cancel fermionic divergences in quantum field theory. Not all of them, of course. The partner degrees of freedom, and is an ingredient supersymmetry for candidates for ultraviolet completions above Planck scale string theory, and could be supergravity also. Of course, supersymmetry must be broken at low energies. I mean, not so low, above the standard model scale. There is already long time ago a proposal for supersymmetric quantum cosmology, and there are some advantages. We will see a little more. They give first order equations, differential equations, instead of second order equations of the second order equation, Wheeler-DeWitt equation. And the Wheeler-DeWitt equation requires boundary conditions. This is a problem, how to choose these conditions. And this supersymmetric quantum cosmology does not require boundary conditions. So, quantum cosmology is a canonical quantization of general relativity, follows from the quantization of the constraints, the Hamiltonian constraint. The momentum constraints lead to a scalar wave function, are solved by a scalar wave function, and usually we don't need them anymore. The wave function depends on the space metric, and we are including a scalar field. It is should be the inflaton. The constraints are implemented in the quantum theory as operator equations, differential equations on this wave function. And as the Hamiltonian vanishes, it gives the Wheeler-DeWitt equation, there is no time-dependent Schrodinger equation, and there is no time. It's a so-called time problem in quantum cosmology. There are many proposals for solutions of this time problem. This wave function, we consider the standard interpretation it gives the probability density to find the universe in some given configuration, space configuration. This wave function, can say it lives on a space slice of the foliation of space-time, and these slices are parameterized by some time, and we take if we take a wave function, we consider wave functions like the one here in this figure, with a series of maxima forming figure like this here. In this case, we will get solutions of this type. In this case, we can take a sequence of these most probable configurations along this maxima and consider it as a trajectory in superspace. Superspace, the superspace of geometrodynamics, the space of the geometric configurations. This has been a proposal by Misner long ago. He called this the parameter of this sort of trajectory super time. So this was a way to introduce a time into quantum cosmology. To such a trajectory corresponds a probability, can be associated a probability and an uncertainty in superspace and also in time could be thought an uncertain time. On the other side, we can give an internal time, any time in the universe by choose of a clock, which should be in one-to-one correspondence to a certain function of the observables of this system. We will require supergravity for our model. As it is well known, supersymmetry relates one bosonic degree of freedom to one fermionic degree of freedom, called partners, superpartners among between them. They can be gauge degrees of freedom or matter. To each degree of freedom, there should be a corresponding one, depending on if it is bosonic or fermionic. In this way, to each field, it's associated a supermultiplet, the field, and its partner. For example, for the tetrad has a partner given by a 3/2 spin field called Rarita-Schwinger field. And this formulation can be done in a so-called superspace. It's not the same superspace of geometrodynamics. It is called the same, but it's different. This superspace has a spin or half variables and transforms, the supersymmetry transformations are given this way here. And supergravity is the general relativity on this superspace. And in this superspace can be given differential, tensor, and integral calculus, and can be constructed an action for supergravity. So in this way, we can construct a supersymmetric quantum cosmology. There are new constraints, Lorentz constraint, and supersymmetric spinorial constraints, which have to be implemented. These spinorial constraints close into the Hamiltonian constraint. In this way, the equations after quantization for these supersymmetric constraints are equivalent to the Wheeler-DeWitt equation, but these are first order equations, and we work this approach for the Friedman-Robertson Lemaitre Walker model with a scalar field. Then we have these superfields. I will not enter into details for this formal part. This is the action, the sum of these two integrals in superspace, and the supersymmetric constraints is here. Okay, there is and this equation and corresponding conjugate one, which I didn't write here. These alpha, beta fermionic quantities are related to the previous ones by these scalings, and they satisfy these Dirac and symmetric brackets. So this can be easily quantized. We take a ground state applied, defined by annihilation operators, alpha and beta, and by the conjugated ones, we generate Hilbert space, and this Hilbert space has positive and negative norms, ghosts. And the general state can be written this way. We implement the constraints, and these constraints give these differential equations, or this coupled equation, and here coupled equation in psi 2 and psi 3, and these decoupled equations which can be solved. These coupled equations we can show that can give solutions which are not normalizable. We require normalizable solutions. So for these two components, we have these solutions here. We don't need any sort of boundary conditions. There are these normalization constants which are fixed by in this way. And from these two ones, only one can be normalizable. We require that the superpotential, this W, cannot be zero, otherwise can be positive, negative, and it defines which one of these two solutions will be normalizable, and we discard the other one. That means we take for it the trivial solution. Then we write the solution this way for a flat space, and we observe that this solution for a fixed scalar field has a Gaussian type form, and it suggests is of this type. If we this solution is of the type I have shown before, of this type, and we can choose the scalar field as a time. We do it, and we define an effective wave function this way.
Excuse me.
Yeah.
Sorry. We are running out of time. Could you make it a little bit faster?
Okay. This corresponds here to a conditional probability, and from it we can compute a mean value for the scalar scale factor. And so in this way we get this mean value, which is an analytic solution with a time given in this way, and we can look for inflationary solutions. We impose restrictions on the super potential for that, and we get, it requires fine tuning for the exit of the inflation. We can do it. And we consider two types of potentials. I show them here. And here in these graphics, we show several cases for scale factor with around 60 e-folds, and the comoving Hubble radius. In this, for these two types of potentials, here and here, and we can see that we can give inflationary scenarios quite realistic in this way for with this time choice, and considering time by the inflaton, and with a satisfactory comoving Hubble radius behavior. Okay, that's all. Thank you.
Any questions? Maybe one quick question. So if no questions, please stop sharing. And we have a little bit of time. I suggest everyone turn on the video and to say hello to each other, and then see you tomorrow. Hi, everyone. This is Wentao. Please turn on the video and say hello to each other, and then let's call it today and see you tomorrow. All right. Why everybody is so shy? All right. Anyways, let's thank all the speakers for this session today, and thank you all. Let's call it today and see you tomorrow. Okay. Bye.
Bye-bye.
Bye.